little bit of a crazy week for myself and a few other faculty. BYU is hosting the Industrial Advisory Board meeting for the eDesign Center. And BYU is part of the eDesign Center. It's headquartered out of Virginia Tech. It has universities like Carnegie Mellon, University of Massachusetts, Amherst, Central Florida, University of Buffalo, Wayne State, a number of other schools that are part of this eDesign Research Center, which is a National Science Foundation sponsored center. Myself and a number of my grad students and some of the undergrad students are basically putting on a two-day conference. It starts tonight with a reception and runs all day tomorrow, pretty much all day on Thursday. We hope to be showing off our multi-user research to a lot of new perspective or potential industries that are coming, like NASA is coming here to look at our research. Lockheed Martin is coming to look at our research, Raytheon, and a number of other companies will be here the next few days. And so if I act or look a little bit on edge, it's probably because I am. I doubt that I'm going to get a lot of sleep the next few days, being kind of the ringleader for this conference. And so if you find that I'm not in my office during office hours, or if I'm rushing too fast to not stop and take time with you, I apologize in advance. Come Friday, hopefully things will go back to kind of a normal.
You're currently the only participant in the conference.
Kind of a normal status, and we'll go from there. Today's lecture, which should have been given last week sometime, but we're a little bit behind, is going to focus on the mathematics of curves, and then we're going to move from that to a discussion of the mathematics of surfaces, to a discussion of the mathematics of solids. The textbook does a pretty good example, or a pretty good effort of covering the mathematics in great depth. We are going to just focus primarily on the Bézier mathematics. The Nerve and B-spline and Hermite mathematics are covered in the book, and you ought to just kind of look and skim those sections, but focus primarily in the Bézier mathematics. There are other courses, 578, that I teach in the graduate area. There is a curve and surface class that Dr. Cederberg teaches in computer science that is an excellent class that goes way beyond kind of the introduction that we give here. The reason we give an introduction here is because this mathematics that we talk about the next few lectures, it's never going to change. It's good, solid mathematics that even 30 years from now, as you're ending your career, that mathematics is going to be there. If you understand the mathematics of curves and surfaces and solids, it is an easy step to move from the interactive development of curves and surfaces to the programmatic development of these kinds of geometries. And so with that, we're going to kind of jump into our lecture. So today's lecture is on curves. If we look at that, we refer to that as what? Equation of a line, but we say it's the what? Point slope. Okay. If we look at this equation, what is that? It's a 2-point equation of a line. Okay. The variable is x and y. If we look at this form, ax plus by equals c, we refer to that as the kind of the standard form, the canonical form of a line. What is the problem with any of these algebraic line representations? They're two-dimensional, okay? And if we were back in the very early days of CAD, these equations would work just fine because they were drafting systems, okay? And we could do that. But we've moved beyond drafting systems to really working in 3D space. So how is a line defined in 3D space? Well, we still need 2 points, P0 and P1, and those are 3-dimensional points. So they should have a bar over the top of them, okay? Not what I wanted. That's what I wanted. So one representation that we could use is P0 plus U times times P1 minus P0, okay? That is the equation of a line assuming that U, our parameter, varies from 0 to 1, okay? If we actually kind of repose that, we could group our P0, so it's P0 times 1 minus U plus P1U, and that is traditionally the representation that you'll find in any textbook is this equation, okay? These two monomials, 1 minus U and U, are referred to as blending functions. It's how the line moves from the beginning point to the ending point. And so if we plotted a curve for 1 minus U, it would start up at 1 and it would dive down to 0, okay? Because U goes from 0 to 1. So when U is 0, we're sitting at point 0, P0. When U is 1, this goes to 0 and we're sitting at the other one. And so if we plot the other blending function, U, it starts at 0 and goes up to 1. Okay? Nothing magic, nothing complex about that, but it's referred to as a parametric line, where U is the parameter. So it's not parametric in the sense that we think of CAD, okay? It's really just a mathematical form of a 3-dimensional line, okay? So here's an example. Let's assume that P0 is 1, 2, and 3. P1 is minus 3, 7, and 3. We put those things into our equation. We end up with kind of 3 equations. Our Px of U is 1 minus 4U. Our Py of U is 2 plus 5U. And our Pz of U is 3. Okay? And we refer to those 3 equations as mapping functions. Okay? And it doesn't matter whether the curve is a line or a very high order complex curve, we're still talking about these 3 equations as mapping functions. They take a parameter, U, and they tell you how it moves in the X space, or how it moves in the Y space, how it moves in the Z space. Okay, how do we get a tangent vector to a curve? How do we do that? Well, in normal mathematics, we take the derivative of the curve with respect to the parameter. Okay? So if we do that and we have some curve let's call it PU as our example here. What we want to do is take kind of the instantaneous change in the slope, and it's a three-dimensional slope that we're doing. Okay, for a line, if the line were just PU, it's going to be what? It's going to be the slope of the line. Okay. So here's our equation. Again, we take the derivative of that with respect to u, and we end up with minus P naught plus P1. So when we put in our points from our previous example, do the mathematics, we end up with a simple number. Okay. So there's nothing very difficult or complex by this. But if we understand this basic parametric line, we should be able to look at second order curves. We should be able to look at third or fourth order curves without too much problem. So a couple of questions. Does it matter what letter we use for the parametric curve? Does it matter whether we call it a capital P, a capital C, a capital Q or T or anything like that? Makes no difference. And as you pick up a book, they will call it by some letter. And you just need to say that's the letter they're using to refer to the curve. Does it matter what parameter they choose? R, S, T, U, V, anything like that? Doesn't matter. Okay? But it varies book by book. Okay? So, for example, in the text, I think the book uses T, if I'm not mistaken. So P naught 1 minus T plus P1T is the same thing that we just talked about a second ago, except our parameter T varies from 0 to 1, and it's still a line. Okay. What is the degree? When we speak of that, what is the degree? It's 1, and we speak of it in terms of what is the order of the variable. So what is the power put on the variable? So in this case, the highest power of T is 1, so the degree of that is 1. In this case, okay, a second order curve, which we have an example of that, okay, ends up with 3 points, okay. So the number of points is related to the degree how? So the order is 1 less than the number of points. Okay? The degree, the order is 1 less than the number of points. What name do we use to give to a third order curve? We call it a cubic. Okay? We call it a cubic curve. So there's our line. The book talks about a Hermite curve. It talks about Bezier curves, which is what we're going to lock in on. It talks about B-spline curves. It talks about NURBS. Okay. Now, if we forget the Hermite for a moment and just look at the bottom 3, do they look similar? What's different about them?
The letter.
There is a B in the Bezier, an N in the B-spline, and an R in the NURB. Okay? And that's really the only difference. The PI is the same I. Okay? So there's something else going on here that we need to understand. And if we can understand what this B is, we get a handle on that, then we should be able to pretty easily understand an N or easily understand an R. Okay? This C, you can think of it as coefficients of a spline. Okay? So this says the summation is just saying it's a collection of terms.